Look up at the night sky. What you're seeing isn't just a scattering of distant lights. Every star, every flicker of cosmic energy is part of an epic story of creation and destruction that stretches back billions of years. These celestial bodies are more than just distant suns. They're the universe's greatest alchemists, forging the very elements that make up our world, our bodies, even the air we breathe. Right now, in the heart of countless stars, hydrogen atoms are squeezed together under unimaginable pressure, transforming into helium, carbon, oxygen, and beyond elements that will one day become part of new planets, new life, even new stars. But how? What cosmic machinery turns the simplest atoms into the building blocks of everything we know? This is the mystery of the stellar forge, the breathtaking process where matter is born, destroyed, and reborn in an endless cycle. Think about the iron in your blood or the calcium in your bones. Those atoms didn't start here on Earth. They were crafted in the cores of ancient stars, then scattered across the galaxy in violent explosions that outshine entire galaxies. Supernova, neutron star collisions, even the slow burn of red giants, each plays a role in this grand recycling project. The universe doesn't waste a single atom. Every speck of dust, every molecule of gas is part of a journey that spans lifetimes longer than human history can even measure. And yet, for all its grandeur, this process is deeply personal. Every time you take a breath, you're inhaling oxygen atoms that were forged in a dying star billions of years ago. The gold in a wedding ring, likely born from the cataclysmic collision of two neutron stars. The universe doesn't just create matter. It transforms it, destroys it, and rebuilds it in ways that defy imagination. So today, we're going to trace that journey from the moment a star ignites to the explosive finale that seeds the cosmos with new possibilities. By the end, you'll never look at the night sky the same way again, because the stars aren't just distant lights, they're the architects of everything. And their story is our story too. Deep in the cosmic darkness, where temperatures hover just above absolute zero, something miraculous begins. Imagine a cloud so vast it could swallow our entire solar system, a swirling sea of hydrogen gas and fine dust particles drifting silently through space. This is where stars are born. Over millions of years, invisible tendrils of gravity start weaving these stray atoms together, gathering them into dense knots. At first, the process is gentle, almost imperceptible. But as more material accumulates, the pull grows stronger and the cloud begins to collapse under its own weight. Within these stellar nurseries, chaos and creation go hand in hand. Turbulence fractures the gas into clumps, while magnetic fields shape their movements like invisible hands sculpting clay. Nearby supernovas send shockwaves rippling through the cloud, compressing pockets of gas until they reach a critical point, the moment when heat and pressure become so intense that hydrogen atoms fuse together in a flash of nuclear fire. And just like that, a star is born. Take the Orion Nebula, one of the most famous stellar nurseries visible from Earth. To the naked eye, it's just a faint smudge in Orion's sword. But through telescopes, we see a dazzling tapestry of newborn stars, some still wrapped in glowing cocoons of gas. Each one is a self-sustaining furnace, where simple hydrogen transforms into heavier elements, lighting up the darkness for light years around. And this isn't some rare event. Every second, somewhere in the universe, another star flickers to life in a cloud just like this one. Yet what's truly astonishing is the scale. A single molecular cloud can spawn thousands of stars at once, each one a potential sun with its own planets, its own story. Some will burn bright and fast, living only a few million years before meeting a dramatic end. Others, like our own sun, will shine steadily for billions of years, nurturing entire solar systems. The universe doesn't just create stars, it creates possibilities. And every atom in those swirling clouds holds the potential to become part of something greater. So the next time you gaze at the night sky, remember, those stars didn't just appear. They were forged in the quiet, cold depths of space where gravity and time work their slow, patient magic. And somewhere out there right now, another cloud is collapsing, another star is igniting, adding its light to the grand cosmic story. Inside every star, there's a battle raging, an eternal tug of war between two cosmic forces. On one side, gravity pulls inward, compressing the star's massive bulk with relentless pressure. On the other, the star fights back with the explosive energy of nuclear fusion, pushing outward with enough force to hold gravity at bay for millions or even billions of years. This delicate balance is what keeps a star alive, and at the heart of it all lies the most powerful process in the universe, the transformation of hydrogen into helium. Picture the core of a star like our Sun, a seething cauldron where temperatures reach 15 million degrees and pressures are 250 billion times stronger than Earth's atmosphere. Here, hydrogen atoms move so fast that when they collide, they don't just bounce off, they merge. 4 hydrogen nuclei, each just a single proton, smashed together in a series of steps called the proton-proton chain. Step 1, 2 protons fuse, turning one into a neutron and releasing a burst of energy. Step 2, another proton joins, forming helium-3, a rare and lightweight version of helium. Finally, when 2 of these helium-3 nuclei meet, they create ordinary helium-4, releasing even more energy and 2 leftover protons to keep the cycle going. It's like cosmic alchemy. Every second, our Sun converts 600 million tons of hydrogen into helium in this precise sequence, but not all stars fuse hydrogen the same way. In stars more massive than the Sun, where temperatures soar even higher, a different process takes over. The CNO cycle. Here, carbon, nitrogen, and oxygen act like atomic middlemen, helping hydrogen fuse into helium at an astonishing rate. Think of it like a high-speed assembly line. A carbon nucleus grabs hydrogen protons one by one, transforming briefly into nitrogen, then oxygen, before shedding 2 protons and returning to carbon, all while releasing torrents of energy. This cycle burns fuel so fiercely that massive stars live fast and die young, shining brighter but lasting only a fraction of the time smaller stars do. Yet no matter how powerful, every star's fusion engine has one unavoidable flaw. It's a self-consuming fire. Over time, the core's hydrogen dwindles, leaving behind a growing heap of helium ash. Gravity tightens its grip, and without enough fusion energy to push back, the star begins its slow transformation. For stars like our Sun, this means swelling into a red giant. For heavier stars, it sets the stage for a far more dramatic finale, one that will ultimately seed the cosmos with the elements of life itself. Because when fusion falters, gravity doesn't just win, it reshapes the universe. Most stars in the universe, including our own Sun, live remarkably predictable lives, at least for a while. They settle into what astronomers call the main sequence, a phase where they burn hydrogen into helium at a steady, almost metronomic pace. Picture a candle burning evenly rather than flickering wildly, a cosmic balancing act that can last for billions of years. The key to this stability lies in a star's mass, which acts like a cosmic hourglass, determining not just how brightly it shines, but how long it has until its fuel runs out. Take 2 stars born from the same cloud of gas and dust. One is a behemoth 50 times heavier than our Sun. The other is a modest red dwarf, barely a tenth the Sun's size. Despite their shared origins, their fates couldn't be more different. The massive star burns through its hydrogen like a wildfire, its core raging at unimaginable temperatures. It might shine with the brilliance of millions of suns, but that intensity comes at a cost. It will exhaust its fuel in just a few million years. Meanwhile, the tiny red dwarf conserves its energy like a frugal traveler, barely glowing with a dull red hue. Its small size means gravity squeezes its core just enough to sustain slow, steady fusion, allowing it to outlive every other star in the galaxy by trillions of years. Our Sun sits comfortably in the middle of this spectrum. For 4.6 billion years, it's maintained a near-perfect equilibrium, converting 600 million tons of hydrogen into helium every single second. That might sound like a lot, but the Sun is so massive that it's only used up about half its fuel so far. It still has another 5 billion years left before it exhausts its core hydrogen and begins its next transformation. But even this seemingly eternal stability is misleading because what happens next depends entirely on what's happening now. Every fusion reaction, every burst of energy is quietly shaping the star's future, building up helium, ash in its core like sand piling up in an hourglass. And that's the paradox of main sequence stars. Their steady glow gives the illusion of permanence, but they're always inching toward change. The more massive the star, the faster it races toward its dramatic finale. The smaller ones take their time, burning so slowly that the universe itself might grow cold before they fade. But no star, no matter how stable, can escape the inevitable. Because when the hydrogen runs out, gravity stops playing nice, and that's when the real cosmic magic begins. When a star's core runs out of hydrogen, it doesn't just fade quietly into the cosmic night, it stages one final, spectacular act. The moment fusion slows, gravity gains the upper hand, compressing the core until it grows hotter and denser. But here's the twist, this crushing force doesn't snuff the star out. Instead, it ignites a new chapter. The star's outer layers, no longer held back by the same outward pressure, expand like a balloon caught in a furnace, swelling hundreds or even thousands of times its original size. This is the red giant phase, a cosmic metamorphosis where aging stars transform into blazing behemoths. Take Betelgeuse, the fiery shoulder of the constellation Orion. This red supergiant is so colossal that if it replaced our Sun, its outer edges would stretch beyond the orbit of Jupiter. Its surface, cooler and redder than a younger star's, pulses like a slow, unstable heartbeat, a sign of the turmoil within. Inside, the star's core, now rich with helium ash, reaches scorching temperatures over 100 million degrees. At these extremes, helium atoms begin fusing into carbon, unlocking a new source of energy. For stars like Betelgeuse, this isn't the end, it's a second wind. But the real magic happens in the details, in a process called the triple alpha reaction. 3 helium nuclei, also known as alpha particles, collide in a precise sequence. 2 fuse first, forming an unstable beryllium nucleus that lasts just a fraction of a second. If a third helium nucleus strikes before the beryllium falls apart, they combine into carbon, releasing a surge of energy. It's a delicate dance, one that requires perfect timing and extreme conditions. Yet this fleeting reaction is why carbon exists at all, the very element that forms the backbone of life on Earth. For heavier stars, the journey doesn't stop there. As carbon accumulates, the core contracts again, reaching even higher temperatures. Now, carbon atoms begin fusing into neon, then oxygen, then silicon, each step building heavier elements like layers in an onion. Near the end, the star's core resembles a cosmic forge, with shells of different elements burning at different depths. Oxygen fuses into silicon, silicon into iron, each reaction releasing less energy than the last. And here's the catch, iron is fusion's dead end. Unlike lighter elements, fusing iron doesn't release energy, it consumes it. When iron dominates the core, the star's fate is sealed. This expansion isn't just about size, it's about legacy. Red giants and supergiants are cosmic recyclers, their outer layers brimming with newly forged elements. Stellar winds carry carbon, oxygen, and nitrogen into space, seeding nearby clouds with the raw materials for new stars, planets, and even life. In a very real sense, the breath in your lungs and the calcium in your bones were once stardust drifting in the atmosphere of an ancient red giant. But this phase, as breathtaking as it is only the calm before the storm, because when iron fills the core, the star's next act will be the most violent of all. Not all stars go out with a violent explosion. For those like our Sun, the final act is more like a slow, breathtaking exhale, a last gasp of beauty before the lights dim forever. When a low or medium mass star reaches the end of its red giant phase, something extraordinary happens. The outer layers, no longer bound tightly by gravity, drift away in shimmering waves of gas and dust, illuminated from within by the star's exposed core. This is the birth of a planetary nebula, a fleeting cosmic masterpiece that glows for just a few tens of thousands of years before fading into the darkness. One of the most famous examples is the Cat's Eye Nebula, a swirling labyrinth of gas that resembles the slit pupil of a celestial feline. Its intricate structure, layers of ejected material sculpted by powerful stellar winds, reveals the star's final throes in stunning detail. Then there's the Ring Nebula, a perfect smoke ring of glowing gas that floats in the constellation Lyra like a cosmic fingerprint. These aren't just random shapes. Each ripple, each tendril of light tells the story of the star's death throes, as turbulent forces and magnetic fields shape the expanding debris into otherworldly forms. But here's what makes planetary nebulae truly remarkable. They're not just stellar tombstones. The material they eject, carbon, oxygen, nitrogen, drifts through space, mingling with interstellar clouds. These atoms, forged in the star's core over billions of years, become the ingredients for new stars, new planets, even new life. The iron in your blood, the oxygen in your lungs, the calcium in your bones, much of it was once part of a dying star's farewell performance. At the center of it all, the star's core remains, exposed and searingly hot. No longer able to sustain fusion, it collapses into a white dwarf, a dense, Earth-sized ember that will slowly cool over trillions of years. Yet, even in this faded state, it retains a surprising influence. The ultraviolet radiation it emits lights up the surrounding nebula like a cosmic lantern, creating the vibrant colors we see from Earth. Without this final burst of energy, planetary nebulae would remain invisible, their beauty hidden in the darkness, so while the star itself may be gone, its impact lingers. The elements it created enrich the galaxy, the light it unleashed paints the cosmos, and the nebula it left behind serves as a reminder. Even in death, a star gives birth to something new. The universe doesn't say goodbye, it just transforms. White dwarfs are the universe's quietest paradoxes, stellar corpses that glow with fading heat, yet pack unimaginable density into their Earth-sized frames. Picture a dying star that's collapsed to the size of our planet, but retains half the mass of our Sun. The physics at play here boggle the mind, matter squeezed so tightly that a single sugar cube's worth would outweigh an adult elephant on Earth. This incredible compression happens because the star's core, no longer supported by fusion, gets crushed by gravity until quantum forces push back, creating a bizarre state where atoms are packed wall to wall, electrons whirling at nearly light speed to prevent total collapse. Some white dwarfs refuse to fade quietly. In binary star systems where two stars orbit each other, a white dwarf can become a cosmic vampire, slowly stealing hydrogen from its living companion. This stolen gas accumulates on the dwarf's surface, building pressure until it reaches a critical threshold. Then, in a blinding flash, the hydrogen ignites in a runaway thermonuclear explosion called a nova. Unlike supernovae that destroy their host stars, these eruptions are surface-level events. Think of them as stellar hiccups rather than death throes. The dwarf survives to feed again, sometimes repeating this cycle for thousands of years. But the most dramatic fate awaits white dwarfs that gorge beyond their limits. If a dwarf pulls enough matter to approach 1.4 times the Sun's mass, a threshold called the Chandrasekhar limit, it undergoes total collapse. The sudden compression triggers runaway fusion that rips the star apart in a Type Ia supernova, an explosion so perfectly calibrated that astronomers use these standard candles to measure cosmic distances. What's astonishing is that these blasts forge iron group elements in abundance, the very metals that make up Earth's core and the steel in our cities. Even solar white dwarfs tell compelling stories. As they cool over billions of years, their carbon-oxygen interiors may crystallize into diamond-like structures, literal stellar gemstones the size of planets. The oldest known white dwarfs, their heat nearly spent, glow faintly in ultraviolet like cosmic fireflies. These ancient remnants are time capsules from the early universe, holding clues about the first generations of stars. And when their light finally winks out, their material remains, drifting among the gas clouds where new stars form, closing the loop on a cycle that spans eons. So while they may seem like cosmic afterthoughts, white dwarfs are anything but insignificant. They're the universe's recyclers, its timekeepers, and even its alchemists, transforming stolen gas into new elements one explosion at a time. Their slow fade into darkness isn't an ending. It's just another transformation in the endless dance of matter. When a star many times more massive than our Sun reaches the end of its life, it doesn't fade, it detonates with the energy of billions of hydrogen bombs, tearing itself apart in a supernova. These explosions are so bright they can briefly outshine every star in their host galaxy combined. But what makes them truly remarkable isn't just their power, it's what they leave behind. Supernova come in two distinct flavors, each with its own apocalyptic recipe. First, there are core collapse supernova, the fate awaiting stars at least 8 times heavier than our Sun. When such a star builds up an iron core, fusion's dead-end gravity suddenly wins the battle it's been fighting for millions of years. The core implodes at nearly 1/4 the speed of light, squeezing protons and electrons together until they form neutrons, releasing a flood of neutrinos. These ghostly particles carry away so much energy that the star's outer layers rebound in a shockwave of destruction, blasting stellar material outward at speeds exceeding 30,000 kilometers per second. Then there are thermonuclear supernova, known as Type Ia, where a white dwarf star steals enough matter from a companion to cross the Chandrasekhar limit. The entire dwarf, now a ticking carbon bomb, undergoes runaway fusion, incinerating itself completely. Unlike the messy core collapse variety, these explosions are remarkably consistent in brightness, making them cosmic mile markers for measuring the universe. Both types are element factories. Core collapse supernova forge elements from oxygen to iron in their final moments, while the incredible heat of a Type Ia explosion creates heavier atoms like gold, platinum, and uranium. The Crab Nebula, that wispy remnant in Taurus, showcases this process in action. When Chinese astronomers recorded its explosion in 1054, they called it a guest star visible even in daylight. Today, we see its expanding debris cloud still glowing from the neutron star's fierce energy at its heart, a pulsar spinning 30 times per second. Without these violent deaths, the periodic table would be nearly empty. The calcium in your teeth, the iodine in your thyroid, even the zinc that helps you taste, all were likely forged in supernova explosions that predate our solar system. These aren't just endings, they're the universe's way of turning destruction into creation, scattering star stuff across the cosmos so new worlds and new life can begin. Imagine taking the entire mass of our Sun and crushing it down into a sphere the size of Manhattan. That's the mind-bending reality of a neutron star. These cosmic leftovers are born from the most violent deaths in the universe, when massive stars explode as supernova and their cores implode under unimaginable pressure. Inside that collapse, atoms themselves surrender to gravity's grip. Protons and electrons forced together so violently they merge into pure neutrons. The result: an object so dense that just a teaspoon of its material would weigh 1 billion tons on Earth, crushing any container we could imagine. But neutron stars aren't just static relics. Many of them spin at dizzying speeds, becoming cosmic lighthouses known as pulsars. Picture a star rotating hundreds of times per second, hurling focused beams of radiation from its poles like a runaway spotlight. When those beams sweep across Earth, we detect them as rhythmic pulses of radio waves, X-rays, or even visible light. The Crab pulsar, the spinning heart of the supernova observed in 1054, blinks at us 30 times every second with near-perfect precision, a celestial metronome keeping time across 1,000 years. Some pulsars take this precision to extremes. Millisecond pulsars, spinning faster than blender blades, owe their speed to stolen energy. They're cosmic vampires that siphon gas from companion stars, revving up their rotation until they become the most accurate clocks in the universe. Astronomers use their steady pulses to test Einstein's theory of relativity and even navigate spacecraft. Then there are the neutron stars that don't dance alone. In rare, catastrophic encounters, two of these ultra-dense objects spiral toward each other, warping space-time so violently they send ripples across the cosmos. Gravitational waves we can now detect here on Earth. Their collision isn't just a spectacle, it's a cosmic alchemy lab. The incredible forces at play forge heavy elements like gold, platinum, and uranium in seconds, scattering them into space. That gold ring on your finger, its atoms were likely born in a neutron star collision billions of years before our solar system existed. From pulsars keeping cosmic time to collisions crafting the universe's rarest elements, neutron stars prove that even in death, stars continue to shape the cosmos in ways we're only beginning to understand. Black holes are the universe's most enigmatic predators, cosmic traps where gravity wins the ultimate battle, bending the rules of space and time until even light cannot escape. Picture this: a star 20 times more massive than our Sun collapses in on itself, its core crushed into a point of infinite density called a singularity. The boundary marking the point of no return, the event horizon, is where the universe as we know it ceases to exist. Cross that invisible threshold and there's no coming back. Time distorts, stretching seconds into eternities. Space curves so severely that all paths lead inward. This isn't just destruction, it's physics pushed to its breaking point. Yet black holes aren't merely cosmic vacuum cleaners. Their influence stretches far beyond their event horizons. Take Sagittarius A, the supermassive black hole anchoring the Milky Way. 4 million times heavier than our Sun, it lurks silently at the galactic center, its gravity choreographing the orbits of billions of stars. Far from chaotic, this gravitational dance may be the reason galaxies like ours hold their shape instead of scattering into the void. Some scientists even argue that without these colossal anchors, galaxies and the stars within them might never have formed in the first place. Then there's the paradox of their creativity. While black holes devour matter, they also eject it at near light speed in searing jets of plasma. These beams, powered by the black hole's spin, can stretch across thousands of light years, heating interstellar gas and triggering star formation in distant clouds. The same force that annihilates also jumpstarts new beginnings. Even Hawking radiation, the faint glow predicted to escape black holes over eons, hints at their role in the universe's grand recycling scheme. But the strangest twist lies in what they leave behind. When two black holes collide, they ripple the fabric of space-time itself, sending gravitational waves echoing across the cosmos. These waves, first detected in 2015, carry secrets about black holes' origins, their growth, and even the nature of gravity. Far from being simple destroyers, black holes are cosmic architects, shaping the universe in ways we're only beginning to decode. So while they may erase matter from one chapter of existence, they're quietly writing new ones in the stars beyond. That carbon atom in your skin, the oxygen in your breath, none of it is truly new. Every atom in your body has been on an epic journey across space and time, passing through the hearts of stars and the chaos of supernova long before Earth even existed. Let's follow one of those atoms, a humble carbon nucleus, as it makes its way from a dying star to you. Our story begins in the final days of a red giant, a star much larger than our Sun. Deep in its core, where temperatures soar past 100 million degrees, 3 helium nuclei collide in a split-second dance called the triple alpha process. In that fleeting moment, they fuse into carbon, the same element that now forms the backbone of your DNA. But this newborn carbon atom isn't destined to stay trapped in the star's core for long. As the red giant convulses in its death throes, powerful stellar winds blast its outer layers into space, carrying our carbon atom into the void. For millions of years, it drifts through the cold, dark interstellar medium, a solitary speck in a vast molecular cloud. Then, a shockwave from a nearby supernova ripples through the cloud, compressing the gas and triggering the birth of a new star. Our carbon atom, now part of a swirling disk of dust and gas, begins to clump together with other atoms. Gravity works its magic, pulling these fragments into larger and larger bodies until, like cosmic Lego, they form rocky planets. One of those planets is Earth. But the journey isn't over yet. That carbon atom might spend eons trapped in Earth's crust, locked in limestone or buried deep in coal. Volcanic eruptions, erosion, or even the slow churn of tectonic plates could eventually set it free again. Then, one day, it's absorbed by a plant through photosynthesis, becoming part of a leaf. A deer eats the leaf, a human eats the deer, and suddenly, that same carbon atom, forged in a star's fiery core billions of years earlier, is part of a living, thinking being. This isn't poetic exaggeration, it's hard science. Nearly every atom heavier than hydrogen and helium in your body was created in stars. The nitrogen in your DNA, the iron in your blood, even the calcium in your bones, all of them were scattered across the galaxy by dying stars, only to be swept up by our infant solar system 4.5 billion years ago. The universe doesn't believe in waste. It's a master recycler, turning stardust into planets, oceans, and life itself. So when you look up at the night sky, remember, you're not just observing the cosmos. You're made from it. Those distant stars aren't just points of light, they're your ancestors. And somewhere out there, new stars are forging atoms that will one day become part of worlds and beings we can't even imagine. The cycle never ends. From death comes new life, from destruction comes creation, and from the hearts of ancient stars comes the very stuff of you. Imagine a cosmic puppeteer, invisible yet powerful enough to sculpt the universe. This is dark matter's hidden role in star formation. Though we can't see it, touch it, or even detect it directly, its gravitational grip shapes everything from spinning galaxies to the stellar nurseries where stars ignite. Picture a vast, unseen scaffold woven through space, its gravity pulling ordinary matter, hydrogen, gas, and dust into dense pockets where gravity can work its magic. Without dark matter's influence, the gas clouds that birth stars might never have clumped together, leaving the cosmos a scattered, starless void. Take the Milky Way as an example. Visible matter, stars, gas, planets accounts for less than 15% of the galaxy's total mass. The rest, an enigmatic halo of dark matter, its gravity acting like an invisible hand that keeps our galaxy from flying apart as it spins. This hidden structure doesn't just hold galaxies together, it guides their very architecture. Where dark matter clusters most densely, its gravity attracts streams of gas, compressing them until they fragment into stellar nurseries like the Orion Nebula. In essence, dark matter is the unseen architect, drafting the blueprints for star formation long before the first hydrogen atom collapses into a protostar. Yet dark matter's story is far from straightforward. In dwarf galaxies where dark matter dominates, star formation should theoretically run wild under such intense gravitational pull. Instead, many of these small galaxies produce fewer stars than expected, a paradox that hints at dark matter's complex relationship with ordinary matter. Some theories suggest dark matter particles might interact weakly with gas, subtly slowing its collapse. Others propose that fierce stellar winds from newborn stars push back against dark matter's grip, creating a cosmic tug-of-war that regulates star birth. The deeper mystery lies in what dark matter actually is. Is it a sea of exotic particles left over from the Big Bang, a flaw in our understanding of gravity itself? Every galaxy's rotation, every cluster's gravitational lensing effect whispers clues, but the answer remains just out of reach. What's undeniable is its legacy. The iron in your blood, the silicon in Earth's crust, even the oxygen filling your lungs, all exist because dark matter's invisible scaffolding guided the gas that forged them. The universe's grand stellar forge doesn't operate alone. It has a silent partner, one we're still struggling to comprehend, and perhaps that's the most humbling thought of all. The very forces that crafted the stars, the planets, and us remain shrouded in shadow. Dark matter doesn't just shape the cosmos, it reminds us how much we have yet to discover. The space between stars may look like an endless void, but it's actually a swirling cosmic soup, a diffuse mixture of gas, dust, and complex molecules that serves as the universe's ultimate recycling bin. This interstellar medium isn't just leftover debris, it's the primordial broth from which every new generation of stars is born. Picture it like a vast, invisible weather system, where temperatures range from a few degrees above absolute zero in the darkest clouds to millions of degrees in supernova-blasted bubbles. Take the iconic pillars of creation in the Eagle Nebula, those towering columns of gas and dust immortalized by the Hubble Space Telescope. What looks like a still image is actually a snapshot of a violent construction site. Ultraviolet radiation from nearby young stars bombards the pillars, eroding them like sand sculptures in a cosmic wind. But this isn't pure destruction. The same radiation that strips away material also compresses the denser regions inside, triggering pockets of gas to collapse under their own gravity. Right now, hidden within those pillars, protostars are flickering to life, their birth catalyzed by the very forces that seem to tear the nebula apart. The interstellar medium works in cycles, each phase more dramatic than the last. When a massive star dies in a supernova explosion, the shockwave rips through nearby gas clouds at hypersonic speeds. These expanding shells of material act like cosmic snowplows, sweeping up interstellar matter and packing it into dense, cold clumps. It's nature's ultimate pressure cooker. The more material gets squeezed together, the more gravity takes over until entire regions become stellar nurseries. The Orion Molecular Cloud Complex, a star-forming region just 1,500 light-years away, shows this process in action. There, supernova remnants from long-dead stars have compressed the gas into finger-like filaments, each one a potential birthplace for hundreds of new suns. But the interstellar medium isn't just about brute force. Chemistry plays a starring role too. In the frigid depths of dark nebulae, where temperatures hover near -260 degrees Celsius, simple atoms stick together to form complex molecules: water, ammonia, even organic compounds like methanol. These microscopic building blocks cling to dust grains, forming icy mantles that will one day vaporize into the atmospheres of newborn planets. Some scientists believe the ingredients for life itself may have first assembled in these frozen interstellar laboratories long before Earth existed. What's truly astonishing is the scale of this recycling program. The oxygen you're breathing right now was once part of a molecular cloud like the one forming stars in Orion. The carbon in your cells might have spent millions of years as a speck of dust drifting between the stars before getting swept up in the solar system's birth. The universe wastes nothing. Every atom expelled by dying stars eventually finds its way back into the cosmic cauldron, ready to be forged into something new. And the cycle continues today. Somewhere in our galaxy, a supernova shockwave is plowing through a gas cloud, triggering the next wave of star formation. The pillars we see today will one day be gone, eroded away, or collapsed into new stars, but in their place, fresh structures will emerge. The interstellar medium is the universe's eternal workbench, and the stellar forge never stops creating. Molecular clouds are the universe's cradles, vast, shadowy realms where gravity weaves stars from the faintest wisps of gas and dust. These colossal structures, some spanning hundreds of light years, are so dense that pockets within them block out starlight entirely, creating inky blotches against the Milky Way's glow. But behind that darkness, something extraordinary is happening. Hydrogen atoms, the simplest and most abundant element, pair up to form molecules, while carbon monoxide and other compounds act like cosmic thermometers, radiating away heat and allowing the cloud to grow ever colder. In this frigid state, gravity gains the upper hand, pulling particles together until the cloud fractures into clumps, each one a potential star in the making. Take the Taurus molecular cloud, a stellar nursery just 430 light-years away. Unlike the dramatic pillars of the Eagle Nebula, Taurus is quieter, its star formation hidden beneath layers of dust. Yet within its folds, infrared telescopes reveal newborn stars swaddled in gas, their faint warmth betraying their presence. Some are tiny proto-brown dwarfs, barely massive enough to ignite fusion, while others will grow into sun-like stars. What decides their fate? It all comes down to turbulence and temperature. In calmer regions of the cloud, gas collapses smoothly, forming fewer but heftier stars. Where turbulent motions churn the gas like a stormy sea, the cloud shatters into many smaller fragments, leading to a crowd of modest stars, a cosmic dice roll that shapes entire star clusters. The chemistry of these clouds is just as vital as their physics. Simple molecules like molecular hydrogen act as cosmic glue, absorbing energy and letting gravity work more efficiently. Dust grains, though microscopic, play an outsized role. Their surfaces serve as meeting points where atoms bond into molecules, while their icy coatings later vaporize into the atmospheres of forming planets. Even complex organic molecules like ethanol and formaldehyde have been detected in these clouds, hinting that the ingredients for life might be mixed into stellar nurseries long before planets exist. But the most fascinating twist, these clouds are ephemeral. The very stars they birth will one day tear them apart. Young, massive stars flood their surroundings with ultraviolet radiation, evaporating nearby gas and carving bubbles in the cloud. Supernova finish the job, scattering the remains into the interstellar medium where they'll eventually coalesce into new clouds. It's a cycle as old as the universe itself, one where destruction fuels creation, and every fading cloud leaves behind the seeds of new light. Deep within the swirling chaos of a molecular cloud, gravity's patience pays off. A dense knot of gas, barely visible against the cosmic backdrop, begins its slow collapse, marking the birth of a protostar, the universe's version of a stellar newborn. This isn't a star yet, not quite. Nuclear fusion hasn't ignited in its core, but the transformation has begun. Like a cosmic spider spinning its web, the protostar pulls in surrounding material from a vast disk of gas and dust that spirals around it. This disk isn't just leftovers, it's the raw material for future planets, moons, and comets. But the real drama unfolds above and below the disk, where twin jets of superheated gas erupt like geysers, shooting outward at speeds exceeding 150,000 miles per hour. Herbig-Haro objects are the cosmic graffiti left behind by these violent outflows. Take HH34, a glowing structure in the Orion Nebula resembling a celestial hourglass. The vibrant bow shocks at the tips of its jets aren't just beautiful, they are evidence of titanic collisions. As the jets ram into slower-moving interstellar gas, they heat it to millions of degrees, making it glow in vivid hues detectable by telescopes. These jets aren't random, they're precision tools sculpting the surrounding nebula and even regulating the protostar's growth. Without them, the star might choke on its own infalling material, collapsing under its own gravity before fusion could begin. The physics behind these jets is as fascinating as their appearance. Twisted magnetic fields generated by the protostar's rotation act like cosmic particle accelerators, channeling material along narrow beams and launching it into space. This process isn't just about shedding excess energy, it's a balancing act. The jets carry away angular momentum, allowing the protostar to keep spinning without tearing itself apart. Astronomers call this magnetic braking, a phenomenon that ensures the young star can eventually settle into a stable existence. Yet protostars are anything but uniform. Some, like those in the Taurus cloud, are relatively quiet, gathering mass slowly over hundreds of thousands of years. Others, particularly in crowded stellar nurseries like the Orion Nebula, grow up in violent environments where radiation from neighboring stars strips away their gaseous cocoons prematurely. These differences set the stage for the star's entire life, determining not just its eventual size and brightness, but whether it will host planets rich in organic molecules or become a solitary wanderer. The chaotic ballet of gas, dust, and magnetic fields during this phase leaves an indelible mark on the star's destiny. And here's the astonishing part, we're witnessing this process in real time. The protostar Vela 162334, buried in the Rho-Ophiuchi cloud complex, offers a front-row seat to these early stellar tantrums. Its flickering brightness and erratic jets reveal a system still figuring itself out, a cosmic toddler taking its first unsteady steps toward maturity. These observations aren't just about understanding stars. They're snapshots of our own sun's infancy, a reminder that every star, no matter how serene it appears now, began its life in a storm of chaos and creation. The universe doesn't build stars gently. It forges them in turbulence, shapes them with fire, and prepares them for lifetimes of light. Brown dwarfs are cosmic misfits caught in an identity crisis between star and planet. Born from collapsing clouds of gas like their stellar siblings, these objects never quite gather enough mass to ignite sustained nuclear fusion in their cores. Imagine a celestial object 50 times heavier than Jupiter, yet only a fraction as bright as the smallest red dwarf star. That's the awkward reality of a brown dwarf, too substantial to be a mere planet, but too feeble to shine like a true star. What makes them fascinating isn't just their failure, it's their persistence. Though they lack the fusion engine that powers stars, brown dwarfs glow faintly in infrared light, their warmth a remnant of the gravitational energy that once crushed them into existence. Some, like the nearby WISE 0855, hover at temperatures colder than a winter day on Earth, barely distinguishable from rogue planets drifting through interstellar space. Yet others, especially the younger ones, smolder like dying embers, their atmospheres swirling with storms of molten iron and silicate clouds, weather systems wilder than anything in our solar system. Here's the twist: brown dwarfs might be the galaxy's silent majority. Surveys suggest these dim objects could outnumber ordinary stars by at least half, lurking unseen in the cosmic shadows. The Spitzer Space Telescope has uncovered entire populations of them hiding in plain sight, from solitary wanderers to unlikely pairs orbiting each other in slow gravitational dances. Their prevalence forces us to rethink the cosmic census. What if the universe is teeming with these almost stars, quietly shaping galactic dynamics in ways we're only beginning to grasp? But the real mystery lies in their potential to host worlds. Brown dwarfs, despite their faintness, often possess swirling disks of dust and gas, the same raw materials that form planets around true stars. Could these failed stars cradle rocky worlds in their dim glow? Some astronomers speculate about free-floating exoplanets untethered to any sun, warmed only by the feeble infrared light of a brown dwarf. And if liquid water existed on such a world, perhaps deep beneath an insulating hydrogen atmosphere, might life find a way? It's a tantalizing thought, a twilight biosphere thriving under the dull red gaze of a cosmic outcast. Yet brown dwarfs defy easy categorization. Some exhibit auroras more intense than Earth's, driven not by a solar wind but by charged particles interacting with their powerful magnetic fields. Others, like the puzzling, spectral class-wide dwarfs, blur the line between planet and star so thoroughly that traditional labels fall apart. In their ambiguity, they challenge our definitions, forcing us to ask not just what a star is, but what it means to truly belong in the cosmic order. So while they may never burn bright, brown dwarfs illuminate something far more profound: the universe's knack for filling every possible niche, no matter how obscure. From their stormy atmospheres to their hidden planetary companions, these celestial in-betweeners remind us that nature doesn't follow tidy classifications. It experiments, it adapts, and in the quiet corners of the galaxy, it crafts wonders that defy expectation. Binary star systems rewrite the rules of stellar fate because in these cosmic duos, no star lives or dies alone. Picture two stars locked in an eternal waltz, their gravitational embrace dictating every step of their evolution. While single stars like our Sun follow a predictable life cycle, binary systems introduce chaos, drama, and spectacle. Take Sirius, the dazzling dog star that dominates our winter skies. To the naked eye, it appears as a single brilliant point, but telescopes reveal its secret. A tiny, ultra-dense white dwarf companion, Sirius B, quietly orbiting its larger sibling. This isn't just a celestial oddity, it's a snapshot of stellar interdependence. The dynamics of binary systems hinge on one critical factor: distance. Stars born close together may share material like cosmic vampires, while wide binaries orbit like distant acquaintances, barely influencing each other. In tight pairs, the gravitational tug of war can warp stars into teardrop shapes, stripping gas from one and funneling it onto the other. The result: mass transfer, a process that can dramatically alter both stars' destinies. The heavier star often evolves faster, swelling into a red giant while its companion remains unchanged. But when that giant sheds its outer layers, its exposed core becomes a white dwarf, and the system's balance shifts forever. Some binaries face even more violent futures. If one star is massive enough, its death throes culminate in a supernova explosion, an event so powerful it can fling the surviving star across the galaxy like a celestial slingshot. Astronomers have spotted these runaway stars, their high-speed trajectories betraying the explosive farewell of a former partner. Other systems aren't so fortunate. When both stars are heavyweights, their deaths can leave behind a pair of neutron stars or black holes locked in a decaying orbit. Over millennia, their spiral tightens until, in a split-second crescendo, they collide, shaking the fabric of space-time with gravitational waves detectable across the universe. Then there's the strangest twist of all: stellar resurrection. In some binary systems, a white dwarf siphons gas from its living companion until it reaches a critical mass, igniting a runaway fusion reaction that blows it apart in a Type Ia supernova. These explosions are so uniform in brightness that they serve as cosmic yardsticks, helping astronomers measure the universe's expansion. But they're also element factories, forging and scattering iron, silicon, and nickel across interstellar space, the raw materials for future stars and planets. So while single stars may seem like the universe's default, binaries remind us that partnership shapes cosmic history. From vampire stars stealing lifeblood to neutron star collisions forging gold, these celestial duos prove that gravity doesn't just create stars, it weaves their stories together in ways we're only beginning to understand. And somewhere out there, right now, two stars are circling each other in silence, unaware that their dance will one day set the stage for the universe's next great spectacle. Every star breathes, not with lungs, but with searing gusts of charged particles that flow outward in an endless cosmic exhale. These stellar winds may be invisible to our eyes, but their impact is written across the galaxy in glowing nebulae, sculpted gas clouds, and even the protective bubble that cradles our solar system. The Sun's solar wind, a steady stream of protons and electrons racing outward at nearly 1.6 million kilometers per hour, is the gentlest version of this phenomenon. Yet even this breeze has power. It carves out the heliosphere, a vast magnetic shield that deflects harmful cosmic rays and interstellar radiation, creating a safe harbor for life on Earth. But not all stellar winds are so benign. Massive stars, those behemoths dozens of times heavier than our Sun, unleash winds of unimaginable ferocity. Picture a hurricane made of plasma, where particles scream outward at speeds approaching 3,000 kilometers per second, carrying away entire Earth masses of material in just a few years. These aren't just gentle breezes, they're stellar bulldozers, reshaping their surroundings with brute force. The Pistol star, one of the most luminous known, loses enough mass each year to build 10,000 Earths. That relentless outflow carves vast cavities in nearby gas clouds, triggering shock waves that can spark new star formation even as they erode older stellar nurseries. The chemistry of these winds is just as critical as their force. As they tear through space, they carry heavy elements forged in the star's core: carbon, oxygen, iron, scattering them like cosmic seeds. This isn't just waste, it's the universe's way of recycling. The iconic Veil Nebula, a tangled web of glowing filaments in Cygnus, owes its intricate structure to winds and supernova from long-dead stars, their expelled material now glowing under the ultraviolet light of new stellar generations. Without these winds, the interstellar medium would starve, lacking the enriched ingredients needed to build planets or life. Yet the most surprising role of stellar winds lies in their ability to dictate a star's fate. For aging red supergiants like Betelgeuse, winds act as a cosmic pressure release valve, stripping away outer layers long before the final explosion. The more mass a star loses this way, the less violent its eventual supernova will be, altering not just the death of the star, but the legacy it leaves behind. Some stars, like the unstable luminous blue variable Eta Carinae, experience such extreme mass loss that they've ejected entire nebulae around themselves, shrouding their inevitable collapse in veils of their own making. From gentle solar gusts to the hurricane force outflows of supergiants, stellar winds prove that a star's influence stretches far beyond its light. They're sculptors, recyclers, and even architects of cosmic evolution, silent forces that weave the elements of creation into the fabric of space itself. And every atom they carry holds the potential to become part of something new. Cosmic rays are the universe's high-speed messengers, subatomic bullets racing through space at nearly the speed of light. Born in some of the most violent events imaginable, these particles carry echoes of supernova shockwaves, colliding neutron stars, and even the turbulent hearts of distant galaxies. Every second, thousands of them pierce Earth's atmosphere, invisible yet relentless. Some are mere protons, the stripped-down nuclei of hydrogen atoms. Others are heavier elements like iron or carbon, atom fragments hurled across space by forces we're still struggling to comprehend. Where do they come from? Most cosmic rays originate right in our own galactic backyard, accelerated by the expanding shock fronts of supernova remnants. Picture the Crab Nebula's pulsar spinning 30 times a second, its magnetic field whipping particles to unimaginable energies like a cosmic slingshot. These stellar graveyards act as natural particle accelerators, far more powerful than anything humans have built. But the most energetic cosmic rays, the ultra-high-energy ones, defy easy explanation. Some pack the kinetic energy of a fast-pitched baseball into a single proton, striking the atmosphere with enough force to trigger particle showers visible for kilometers. Their impact on Earth is subtle but profound. As cosmic rays collide with air molecules high above us, they create cascades of secondary particles, muons, pions, and electrons that rain down invisibly. Some scientists believe these collisions might even influence cloud formation, ionizing molecules in the atmosphere and providing seeds for water droplets to form. It's a controversial idea, but if true, it means distant stellar explosions could be subtly shaping our weather patterns. The most fascinating part, cosmic rays are time travelers. Some of the particles hitting us today were flung into space millions of years ago, carrying the elemental fingerprints of ancient stars. By catching them with high-altitude balloons or underground detectors like the Pierre Auger Observatory, we're not just studying physics, we're reading the universe's diary, written in the language of atomic shrapnel. Yet the mystery of the highest energy cosmic rays remains unsolved. Could they come from supermassive black holes at galaxy cores, where magnetic fields twist into cosmic catapults? Or perhaps from the violent mergers of galaxy clusters, where entire clouds of gas are heated to hundreds of millions of degrees? Whatever their source, these particles remind us that the universe is anything but quiet. It's a storm of energy, and we're standing in the rain. Gamma-ray bursts are the universe's ultimate fireworks, brief, blinding flashes of energy so intense they can outshine 1,000,000 trillion suns. In just a few seconds, one of these events releases more energy than our sun will emit in its entire 10 billion-year lifetime. What could possibly power such an unimaginable explosion? The answer lies in the most violent births and deaths in the cosmos, collapsing massive stars, colliding neutron stars, or the sudden formation of black holes. Take the gamma-ray burst GRB 220101A, detected in October 2022. For a fleeting moment, it became the brightest object ever recorded in gamma rays, visible across 9 billion light-years of space. Telescopes caught its afterglow fading across the electromagnetic spectrum, from X-rays to radio waves, revealing a relativistic jet of particles moving at 99.999% the speed of light. These jets, narrower than a pencil beam but stretching billions of kilometers, are the universe's most powerful particle accelerators, natural laboratories for physics far beyond anything we can recreate on Earth. The sheer violence of these events defies intuition. When two neutron stars spiral together and merge, their collision doesn't just produce gravitational waves, it forges a magnetic maelstrom that launches jets of gamma rays and charged particles into the void. Simulations suggest the magnetic fields in these jets are a quadrillion times stronger than Earth's, twisting space-time itself as they punch through surrounding gas. And when a particularly massive star collapses directly into a black hole, the newborn singularity doesn't just swallow matter. It ejects part of the star's core in a hypernova explosion, a supernova on steroids. Yet gamma-ray bursts aren't just cosmic curiosities, they're potential threats. A burst within a few thousand light-years could strip Earth's ozone layer, exposing life to deadly ultraviolet radiation. The Ordovician extinction 440 million years ago has even been tentatively linked to a nearby gamma-ray event. Thankfully, the odds are slim. Most bursts occur in distant galaxies, and Milky Way stellar demographics make a close encounter unlikely. But their existence reminds us that the universe is far from benign. What makes these bursts truly invaluable is what they teach us about extreme physics. Their afterglows serve as cosmic lighthouses, illuminating interstellar gas billions of light-years away. By analyzing how this light dims and shifts, astronomers map the distribution of matter across the universe. Some bursts even help measure cosmic expansion independently of supernova, offering new ways to probe dark energy. And in their relativistic jets, we catch glimpses of conditions that existed microseconds after the Big Bang, temperatures and densities so extreme they defy terrestrial experiment. So while a gamma-ray burst may last mere seconds, its legacy endures. It's a fleeting scream in the cosmic darkness, a beacon from the edge of physics, and a humbling reminder of the forces that shape our universe. Einstein saw the universe not as a static stage, but as a dynamic fabric, one that could stretch, twist, and ripple like the surface of a pond. For a century, his prediction remained just that, a mathematical curiosity. Then, on September 14, 2015, humanity's most sensitive instruments trembled. Two black holes, each about 30 times the mass of our Sun, had collided 1.3 billion light-years away. Their final death spiral sent shockwaves through space-time itself, distortions so subtle they shifted the arms of LIGO detectors by less than 1/10,000th the width of a proton. Yet that minuscule wobble changed everything. For the first time, we'd heard the universe's hidden symphony, the sound of gravity ringing like a bell. These gravitational waves aren't just cosmic vibrations, they're messengers from the stellar forge's most violent workshops. When neutron stars collide, their immense density, a sugar cube's worth of material weighing as much as Mount Everest, creates ripples that compress and stretch spacetime as they race outward at light speed. The event GW190816, detected in August 2017, wasn't just a textbook merger. It forged enough gold and platinum in seconds to outweigh our entire planet, scattering precious metals across the cosmos like a celestial treasure chest bursting open. Suddenly, we understood. The jewelry you wear, the electronics you use, their atoms were likely born in such cataclysmic crashes long before Earth existed. What makes gravitational waves revolutionary isn't just their origin. It's how they travel. Unlike light, which can be obscured by dust or gas, these space-time ripples pass through everything unimpeded. When black holes merge in the void between galaxies, their lightless embrace would be invisible to telescopes, but their gravitational waves, those slice cleanly through cosmic obstacles, carrying secrets from the darkest corners of the universe. It's as if we've been watching a silent movie of the cosmos until now. With gravitational waves, we've finally turned on the sound. The detectors themselves are marvels of ingenuity. LIGO twin observatories in Louisiana and Washington, along with their European counterpart Virgo, function like cosmic microphones. Their laser beams traveling down 4-kilometer-long vacuum tubes act as ultra-precise rulers. When a gravitational wave passes, it momentarily changes the length of one arm relative to the other, a distortion measured with precision equivalent to detecting a human hair's width change in the distance to Alpha Centauri. Future arrays, like the space-based LISA mission, will use satellites millions of kilometers apart to catch lower-frequency waves, ones emitted by supermassive black holes dancing at the centers of galaxies. Each detection peels back another layer of cosmic mystery. The event GW190521 revealed a black hole swallowing a neutron star, a scenario theorists doubted we'd ever witness. Others have uncovered intermediate mass black holes, the missing link between star-sized ones and the supermassive behemoths lurking in galactic cores. With every chirp, every crescendo in the gravitational wave background, we're assembling a new map of the universe, one written not in light, but in the warps and wefts of space-time itself. And this is just the beginning. Hidden in these signals could be echoes from the Big Bang, hints of exotic physics, even evidence of higher dimensions. The stellar forge doesn't just create matter, It bends the very framework of reality, and now at last we're listening. For millennia, planets seemed like rare jewels, precious worlds orbiting our sun and nothing more. But the universe loves variety, and the discovery of exoplanets shattered that illusion, revealing planets so bizarre they defy imagination. Picture a world where diamonds rain from molten metal skies, or a gas giant so close to its star that its atmosphere boils away in a comet-like tail. These aren't science fiction, they're real places, and they're rewriting the rules of planetary science. Finding these worlds requires cosmic detective work. Astronomers don't just point telescopes and snap photos, they read the subtle clues hidden in starlight. When a planet crosses its star's face, the star dims ever so slightly, like a moth flitting past a spotlight. This transit method has uncovered thousands of exoplanets, including the TRAPPIST-1 system's 7 Earth-sized worlds. Another technique, the radial velocity method, tracks a star's rhythmic wobble as an orbiting planet's gravity tugs it back and forth. The HARP spectrograph in Chile has used this approach to find planets so light they could be rocky twins of Earth. But the most mind-bending discoveries lurk around dead stars. Take PSRB 1257+12b, a planet orbiting a pulsar, the corpse of a massive star that exploded in a supernova. This world shouldn't exist. The blast that created its neutron star host should have vaporized any nearby planets. Yet there it is, likely a survivor or a second-generation world born from the debris. Even white dwarfs, the faded embers of sun-like stars, host planets. WD 1856+534b is a gas giant orbiting so close that its year lasts just 1.4 days, skimming the dead star's surface in a gravitational dance that defies expectations. The real question isn't just whether planets can survive stellar death, it's whether life could cling on in such extreme environments. A planet orbiting a pulsar would face lethal radiation, but beneath an ice shell or thick atmosphere, microbial life might endure. White dwarf systems offer a stranger possibility. As the dying star blew off its outer layers, it might have temporarily warmed frozen moons or comets in its outer system, creating transient havens for life. Every exoplanet discovery is a puzzle piece in the grand story of cosmic evolution. From rogue planets drifting between stars to molten worlds tidally locked to their suns, these distant realms prove the universe is richer, wilder, and more inventive than we ever dreamed. And somewhere among them, perhaps, is a world not so different from ours where Stardust has awakened and the universe has begun to know itself. Our sun may seem eternal, burning with steady brilliance day after day, but like all stars, its lifespan is finite, and its final chapters will rewrite the solar system as we know it. Right now, the sun sits comfortably in its main sequence phase, converting hydrogen into helium at a rate of 600 million tons per second. But in about 5 billion years, this familiar stability will shatter. As the core's hydrogen fuel dwindles, gravity will tighten its grip, compressing the sun's heart until temperatures soar high enough to ignite helium fusion. This is the beginning of the end, the moment our star transforms into a red giant. The change won't be subtle. The sun's outer layers will balloon outward, swallowing Mercury and Venus whole. Earth's fate hangs in the balance. Some models suggest our planet might escape engulfment, orbiting just beyond the star's expanding edge, but survival won't mean salvation. The sun's intense radiation will scorch Earth's surface, boiling away oceans and stripping the atmosphere into space. Even if the planet remains intact, it will become a barren, molten rock, a ghost of its former self. Meanwhile, the red giant's violent stellar winds will blast through the solar system, pushing asteroids and comets into chaotic new orbits, disrupting whatever remnants of life might still cling to the outer worlds. But the sun's metamorphosis doesn't stop there. After burning helium for another billion years, the core will exhaust its fuel once more, leaving behind a dense orb of carbon and oxygen, a white dwarf. The outer layers, now untethered by gravity, will drift away in a shimmering veil of gas, illuminated by the dwarfs' searing ultraviolet radiation. This is the birth of a planetary nebula, a fleeting cosmic masterpiece like the Ring Nebula in Lyra. For tens of thousands of years, this glowing shell will expand into space, carrying traces of the Sun's elemental legacy: carbon, oxygen, nitrogen, before fading into the darkness. The white dwarf left behind will be a shadow of the Sun we know. No larger than Earth, but packing half the Sun's mass, it will glow faintly from residual heat, a dim ember cooling over trillions of years. With no energy source left, it will slowly fade, becoming a cold, dead relic, a black dwarf. But long before that happens, the solar system will have transformed beyond recognition. Mars and the outer planets, baked by the red giant's wrath, may orbit a distant, dimmer star, their icy moons thawed and evaporated. The asteroid belt could be scattered, and the Kuiper belt's frozen worlds might find themselves adrift in interstellar space. This isn't just a story of destruction, it's a cycle of renewal. The material the Sun ejects in its death throes will eventually mingle with interstellar clouds, enriching them with the heavy elements needed to form new stars, new planets, and perhaps even new life. The atoms that once warmed Earth could one day become part of another world, another story. The universe thrives on these endings, turning the demise of one star into the birth of countless others. And while our Sun's fate is sealed, its legacy, like all stars, will live on in the cosmos it helped shape. The Milky Way isn't just a static swirl of stars, it's a living, breathing ecosystem where stellar lives unfold in a grand, interconnected dance. From the bustling stellar nurseries in its spiral arms to the ancient stellar graveyards near its core, our galaxy pulses with the rhythms of birth and destruction. Right now, in the Orion Cygnus arm, vast clouds of molecular gas collapse under their own gravity, giving birth to brilliant new stars. Meanwhile, in the Carina Nebula, massive stars blaze through their fuel in mere millions of years, destined to explode as supernova that will seed future generations. This isn't random chaos, it's a finely tuned cycle, one where the death of one star becomes the raw material for the next. Star formation rates aren't uniform across the galaxy. Spiral arms, dense with gas and dust, act like cosmic conveyor belts, compressing material as they rotate. Regions like the Scutum Centaurus arm buzz with activity, churning out hundreds of stars per million years. By contrast, the galaxy's outer fringes and central bulge are quieter. Their gas supplies either too diffuse or already exhausted. But the real surprise lies in the galactic center, where the supermassive black hole Sagittarius A star holds court. Far from being a sterile void, this region hosts intense star formation amidst its turmoil. Young, massive stars orbit perilously close to the black hole itself, defying expectations about how such fragile objects could form in such a violent environment. Supernovas serve as the galaxy's ultimate recyclers, cosmic detonations that inject heavy elements back into the interstellar medium. When a massive star explodes in the Perseus arm, the shockwave ripples outward, triggering nearby gas clouds to collapse into new stars. These explosions don't just spread elements, they sculpt entire regions. The Gum Nebula, a sprawling structure stretching across 40 degrees of the southern sky, owes its existence to ancient supernova whose remnants still glow faintly in X-rays. Even our solar system might owe its existence to such an event. Geochemical evidence suggests a nearby supernova shockwave nudged a collapsing cloud of gas to form the Sun and planets 4.6 billion years ago. Yet there's a lingering question: is the Milky Way's star formation slowing down? Observations suggest our galaxy peaked in stellar births around 10 billion years ago and has been gradually declining since. The reason: a dwindling supply of fresh gas. As stars form, they lock away hydrogen in their cores, and supernova winds can blow remaining gas out of the disk entirely. Without new inflows from intergalactic space, the raw materials for star formation grow scarce. Simulations predict the Milky Way will transition into a red and dead galaxy in the distant future, its spiral arms fading as star birth grinds to a halt. But don't mistake this slowdown for stagnation. Even now, pockets of vigorous star formation persist, like the W43 region near the galactic bar, where massive clusters ignite amidst turbulent gas flows. And when the next supernova lights up our galactic neighborhood, it may well spark yet another wave of creation. The Milky Way's story isn't one of simple decline, it's a saga of ebb and flow, where every ending carries the seeds of a new beginning. From the tiniest protostar to the mightiest black hole, every piece plays its part in this cosmic symphony. Galactic collisions are the universe's most spectacular slow-motion dramas, cosmic ballets where entire islands of stars, gas, and dark matter spiral together over billions of years. What looks like destruction from afar is actually the universe's way of hitting the reset button, triggering bursts of star formation so intense they can outshine entire galaxies. Take the antennae galaxies, two spirals caught in a mid-collision embrace. Their long, streaming tails, stretched by tidal forces, are studded with newborn star clusters, each one containing thousands of young, hot stars. These stellar fireworks don't happen by accident. When galaxies merge, their immense gas clouds slam together, creating shock waves that compress the material into dense knots. Suddenly, gravity gains the upper hand, and entire nurseries of stars ignite at once, turning a quiet galactic neighborhood into a stellar factory. Our own Milky Way is no stranger to this process. The Gaia spacecraft's detailed maps reveal ghostly streams of stars, the shredded remains of smaller galaxies consumed long ago. One of these victims, the Gaia Enceladus galaxy, collided with the Milky Way roughly 10 billion years ago, its stars now scattered throughout our galaxy's halo like cosmic confetti. But the biggest merger is yet to come. Right now, the Andromeda Galaxy, a spiral slightly larger than the Milky Way, is racing toward us at 110 kilometers per second. In about 4 billion years, the two galaxies will begin a gravitational dance that will last for billions more. Initially, they'll pass through each other like phantom stars are so widely spaced that direct collisions are rare. But their immense gas clouds won't be so lucky. When those clouds collide, the real show begins. Simulations show the Milky Way and Andromeda's spiral arms shredding into long arcs, their central black holes whirling toward each other in a deadly spiral. The compressed gas between them will erupt with star formation, creating a dazzling but short-lived starburst phase where new stars form at rates hundreds of times higher than today. For a while, the merged galaxy, dubbed Milkdromeda by astronomers, will glow with the blue light of countless young, massive stars. But these stellar newborns are destined for short, violent lives. Within a few 100 million years, the heaviest will explode as supernova, polluting the galaxy with newly forged metals and triggering yet more rounds of star birth. The aftermath of such mergers is just as fascinating. The chaotic gravitational forces can reshape spirals into featureless ellipticals, smooth, football-shaped galaxies where star formation has largely ceased. Without the organized rotation of spiral arms, gas can't collapse efficiently into new stars. That's why many of the universe's largest ellipticals, like Messier 87 with its famous jet, are red and dead, their star-forming fuel exhausted long ago. Yet even these seemingly lifeless giants hold surprises. Deep within their cores, supermassive black holes merge, sending gravitational waves rippling through space-time. The recoil from these collisions can kick the resulting black hole clear out of the galaxy, leaving behind a dark, starless core. What makes galactic collisions so transformative isn't just the spectacle, it's their role in cosmic evolution. Without these encounters, galaxies might never grow beyond modest clumps of stars. The heavy elements forged in merger-induced starbursts become the building blocks for rocky planets and ultimately life. Even our solar system's existence might trace back to an ancient galactic merger that stirred up the Milky Way's gas, triggering the birth of the Sun. So while the collision with Andromeda lies far in Earth's future, its legacy is already written in the stars above us, a reminder that the universe thrives on chaos and from destruction comes creation. The universe is still young, just 13.8 billion years into a lifespan that could stretch for trillions more. But even now, the signs of change are written in the faint glow of distant galaxies. Every second across the cosmos, stars are converting hydrogen into heavier elements, locking away the fuel for future star formation in stellar cores and the scattered remnants of dead stars. It's a slow drain, but an inevitable one. As the available hydrogen dwindles, the era of starlight, the window of time when new stars ignite regularly, will eventually close. Galaxies like our Milky Way are currently in their star-forming prime, producing several new suns each year. But peer into the future, and this bustling activity will slow to a trickle. Simulations suggest that in about 100 billion years, the universe's star formation rate will plummet to just a fraction of today's levels. The reason? Simple exhaustion. Most of the universe's hydrogen will have been consumed, locked inside aging stars, white dwarfs, neutron stars, or blown into intergalactic space by supernova winds. Without fresh inflows of pristine gas, galaxies can't replenish what they lose. The Milky Way's fate mirrors this cosmic trend. Our galaxy's spiral arms, currently vibrant with stellar nurseries like Orion, will gradually lose their structure as star formation wanes. The remaining gas will either be too hot to collapse or too diffuse to trigger new births. Star-forming regions will shrink toward the galactic outskirts, where cooler, isolated gas clouds might still cling to enough hydrogen to birth the occasional star. Meanwhile, the galaxy's core will grow quieter, its supermassive black hole feeding on dwindling supplies of infalling material. But the real transformation happens on even longer timescales. After trillions of years, the universe will enter the degenerate era, a period dominated by the fading embers of stars that never died. Red dwarfs, the smallest and longest-lived stars, will still glow faintly, burning their hydrogen fuel at miserly rates for up to 10 trillion years. These dim, crimson suns will be the last beacons in an increasingly dark cosmos. Even they, though, are temporary. One by one, they'll exhaust their fuel, cooling into inert black dwarfs, cold, dead spheres of electron-degenerate matter. The last stars to form will likely arise in rare, massive molecular clouds drifting between galaxies. These rogue gas pockets, untouched by earlier star-forming frenzy, might ignite feeble stellar flames long after mainstream galaxies have gone dark. But these latecomers will be outliers in a universe where starlight is the exception, not the norm. What happens when even the final red dwarfs flicker out? The universe won't vanish, it will simply transition into a new phase. Black holes will dominate, slowly evaporating via Hawking radiation over incomprehensible timescales. The scattered remnants of planets and dead stars will drift farther apart as the universe expands, their atoms decaying into subatomic particles. It's a lonely, quiet future, one where the vibrant stellar nurseries and brilliant supernova of today are distant memories. Yet this bleak vision holds a strange beauty. Every atom forged in those long-dead stars will still exist, woven into the fabric of space itself. The universe doesn't truly end, it transforms. And who knows, in some distant corner of space-time, conditions might align once more, igniting a new cycle of creation. The story of star formation isn't just about beginnings and endings. It's about the universe's relentless capacity for change. Dark energy is the universe's silent puppeteer, an invisible force stretching the cosmos apart at an ever-increasing pace. Imagine a loaf of raisin bread baking in an oven where each raisin represents a galaxy. As the dough expands, the raisins move farther apart. Now picture that oven heating up faster and faster, stretching the dough so rapidly that eventually no raisin will ever see another again. That's the chilling reality dark energy imposes on our cosmic future. Discovered in the late 1990s when astronomers noticed distant supernovae were fainter than expected, this mysterious force now dominates the universe's energy budget, accounting for nearly 70% of its content. Yet we still don't know what it is. The consequences of this unchecked expansion are profound. Over billions of years, galaxies beyond our local group, already racing away at unimaginable speeds, will vanish from view entirely. Their light, stretched beyond detectability by the expanding space between us, will fade into infrared oblivion. Future astronomers, if any exist, will peer into a sky nearly empty of galaxies, with only the dim glow of nearby stars to remind them of the universe's former brilliance. Even more unsettling, this expansion isn't just moving galaxies apart, it's tearing apart the very fabric of the cosmos. In a scenario called the Big Rip, dark energy's grip could grow so strong that it overcomes all other forces, shredding galaxies, then stars, and eventually atoms themselves in a final, catastrophic moment. Is there any hope against this cosmic exile? Some theorists speculate about phantom energy, a hypothetical form of dark energy that grows stronger over time, potentially dooming the universe to that violent end. Others suggest dark energy might weaken or even reverse, allowing gravity to regain control in a big crunch. Yet the most plausible models paint a quieter, lonelier picture, the heat death, where expansion continues indefinitely, stars burn out, and the universe cools into a featureless void. But here's the twist: dark energy might also hold clues to new physics. If it's a manifestation of vacuum energy, the inherent energy of empty space, it could hint at undiscovered quantum fields permeating the cosmos. Alternative theories propose modifying Einstein's gravity itself, rewriting the rules on cosmic scales. Experiments like the Dark Energy Survey and future missions such as the Euclid telescope are mapping billions of galaxies to trace dark energy's footprint through time. Each dataset peels back another layer of the mystery, probing whether this force is truly constant or evolves as the universe ages. For now, dark energy remains one of science's greatest enigmas, a reminder that the universe's grandest processes are often its most elusive. Yet in its relentless push, it's also writing the final chapters of the stellar forge, determining whether the cosmos will fade gently into night or meet a more dramatic finale. Either way, the story isn't over yet. Billions of years from now, long after Earth is gone, the last stars may still flicker in isolated pockets of the universe, their light a fading echo of the brilliant cosmic dawn we witness today. The elements pulsing through your veins, carbon, oxygen, nitrogen, were forged in the hearts of long-dead stars. This cosmic ancestry connects every living thing on Earth to the stellar forge, raising a tantalizing question. If stardust could spark life here, could it have ignited elsewhere in the universe? Astrobiologists are piecing together this puzzle by hunting for worlds where the chemistry of life might find a foothold. Take the exoplanet K218b, orbiting a red dwarf star 110 light-years away. When telescopes detected water vapor in its atmosphere, it wasn't just a scientific breakthrough, it was a glimpse into a realm where stellar alchemy might have brewed the ingredients for life beyond our solar system. But what makes a world truly habitable? Distance from its star is just the beginning. A planet needs liquid water, yes, but also the right mix of elements and energy sources to sustain biochemistry. Around white dwarfs, the dense cores of extinct sun-like stars, scientists have theorized about ghost planets, survivors of their star's violent red giant phase that now orbit in a dim afterlife. Though bathed in faint ultraviolet light, these worlds might retain enough heat beneath icy shells to host subsurface oceans, much like Jupiter's moon Europa. Even neutron stars, those city-sized remnants of supernova, could theoretically support life on planets heated not by starlight, but by the star's relentless X-ray emissions. Radiation that would sterilize Earth might power photosynthesis for exotic organisms adapted to thrive in such extremes. The search for these cosmic oases hinges on biosignatures, chemical clues imprinted in a planet's atmosphere. Oxygen, for instance, is highly reactive and disappears quickly unless replenished, possibly by life. When the James Webb Space Telescope analyzed the atmosphere of exoplanet WASP 96b, it wasn't just looking for water, it was hunting for unexpected molecular pairs like methane and oxygen that rarely coexist without biological activity. Other potential markers like phosphine, a gas produced by microbes in Earth's swamps, were famously detected in Venus's clouds, sparking debates about whether rocky planets closer to home might harbor aerial life. Yet the ultimate test may lie beyond chemistry. Some propose technosignatures evidence of advanced civilizations, like artificial megastructures or laser pulses. The bizarre dimming of Tabby's star, once theorized to be caused by an alien Dyson swarm, reminds us that life might not always look familiar. From extremophiles in neutron star systems to silicon-based organisms thriving in scorching acid clouds, the universe's imagination could dwarf our own. Every new exoplanet discovered expands the canvas of possibilities. With over 5,000 confirmed worlds and billions more awaiting discovery, the stellar forge's greatest masterpiece might not be stars or nebulae, but the life it unknowingly seeds across the cosmos. And if we ever find it, we'll have answered not just a scientific question, but a deeply human one. In a universe built from stardust, are we truly alone? From the fiery birth of stars in swirling molecular clouds to the cataclysmic explosions that seed the cosmos with heavy elements, the stellar forge is the universe's greatest architect. It takes the simplest atoms, hydrogen and helium, and transforms them into the building blocks of planets, life, and even new generations of stars. This grand cycle of creation and destruction isn't some distant cosmic phenomenon, it's personal. The oxygen you're breathing right now was forged in the heart of a dying star billions of years ago. The iron coursing through your blood was likely born in the violent collision of two neutron stars. Every piece of you, from the calcium in your bones to the carbon in your cells, carries the signature of ancient stellar alchemy. Looking up at the night sky isn't just stargazing, it's time travel. When you admire the glow of Orion or the shimmering band of the Milky Way, you're seeing snapshots of stellar lives at different stages, that faint red ember. An aging giant nearing the end of its journey, the brilliant blue spark, a young, massive star burning fast and furious. Even the dark patches between the stars hold secrets, veils of dust and gas where future suns are taking shape right now, unseen by human eyes. The universe isn't static, it's a living, breathing network of interconnected stories, each star a character in an epic that spans billions of years. And the most humbling thought, this cosmic dance is far from over. Right now, somewhere in the depths of space, a supernova shockwave is compressing a gas cloud, triggering new star birth. A white dwarf is siphoning material from its companion, inching toward a cataclysmic explosion. A pair of black holes spiral toward each other, preparing to send ripples through the fabric of space-time. We're witnessing just one frame in a movie that never ends, a universe where matter is endlessly recycled, transformed, and reborn. So the next time you feel small under the vast night sky, remember, you're not separate from the cosmos. You're made of it. The same forces that shape galaxies and ignite stars also shaped you. In a very real sense, we are the universe experiencing itself. If that doesn't fill you with wonder, nothing will. If this journey through the stellar forge sparked your curiosity, don't keep it to yourself. Hit like, subscribe, and share your thoughts in the comments. What cosmic mystery fascinates you most? The violent beauty of supernova, the eerie glow of nebulae, the possibility of life on distant worlds? Let's keep the conversation going. Until our next adventure among the stars, keep looking up, because the universe has endless stories left to tell.